What's up, everybody? This is Matt Brown with another IoT hacking video. Today we are taking a look at a Wi-Fi router. This is the Mojo C-75. This is an enterprise grade wireless router that's meant for coverage of large areas, and today we are going to begin an adventure to dig into this device and try to get its firmware with the eventual goal of getting a root shell. You may have seen some of my past videos where one video we get a root shell out of the thing. Not going to be that easy on this device because we are going to experience something that I've seen on a number of devices out there. We are going to get some kind of a shell environment, but it's not going to be a full administrative root shell, and so we are going to have to pivot or escalate our way up to that root access in subsequent videos. But today we are going to show the dumping of the firmware and that limited console access that I talked about. To get that console access, we're going to use something that might be a blast from the past for some of you people. This is an RS-232 cable. This is an old school serial cable. You may have seen on my other videos, kind of just the UART cable where I'm connecting up to pins on a PCB, but this is using the old school serial port on my adapter. Now we're going to connect up to our device with an Ethernet port, and then I have this nice little adapter that will convert that to USB and actually show up as a device on my my modern workstation here that does not have an RS-232 port on it. Sadly, they don't still put those on these systems. Let's go over to the bench and take a look at what I have over here. All right, so I've already taken the device out of the case, and I'm just going to show part of that case right here. You can see that we have a number of Ethernet jacks, and one of them is labeled console. And so the first thing we're going to do is we're going to plug in this console cable that we talked about, and we're going to plug the other end on my USB hub up here. And then we're going to power this thing on and see what happens. Take gloves off for just a second. All right, so we're going to head over to my computer here, and I can run dmessage really fast, and we'll see that I've got a new device right here, this PL2303 cable. So that is that RS-232 cable, the adapter cable, and it's showing up under TTY USB 0. And as always, so we're going to use picocom. We're going to set the baud rate to the default baud rate. You should always be guessing first if you don't know what the baud rate is. And then we are going to get this ready. So we open up that terminal, and now I'm going to power on my device, and we're just going to let it boot up, and we're going to see what happens. So on this device, it's not that interesting. I can actually hold down enter here, and I can pause the boot and get into U-boot, but it is an extremely limited U-boot menu, the commands that I have available there. I actually can't dump the firmware from the U-boot on this system. So I'm going to scroll up in this boot process and notice something here. So here it's saying that there's actually two MTD devices that are being recognized by the system. So one of them has 5 partitions, and another one has 1 partition. So here we see kind of your standard, U-boot, some environmental variables, a kernel, a root file system. This ART partition is for like wireless calibration. Not super interesting to us today. And then on this other chip, we see this OPT, this opt partition, which looks like that's going to be where any writable data is going to live. Just just based on some background I have with these embedded systems, oftentimes the root file system is going to be a read-only file system to keep the firmware stable. But that means it needs somewhere to write data to, so that leaves this as kind of the only option. So I am going to scroll down here, and it's still in the process of booting up. I'm going to try to hit enter, and I get a prompt. Now, when reading the documentation for this device, it gives credentials, right? It says, hey, the default credentials that it provides are that you can log in as the config user with the password config. And then I get given this shell environment. It says, welcome to the sensor config shell. And that's pretty interesting because this is not your standard, bash shell or something like that. This is a restricted shell that is custom to this device, right? So I can type the help command, and you can see I get a very custom set of commands that are non-standard. And then interestingly down here, I do get some commands that look a little bit more familiar to me. The password command, ping, things like that. Now, there definitely can be vulnerabilities that will allow you to escape out of a limited shell like this and try to get to a more fully featured shell like bash, sh, something like that. But I have not found any of those vulnerabilities in my poking around initially at this device. And the best chance that I'm going to have is to pull the firmware off of this device initially to get the source code or whatever is running. I scrolled past it. This sensor config shell is what it's calling it. Well, it would be really nice for me to have the source code, the script code to whatever this environment is, because otherwise I would just be doing black box testing, which is going to be pretty hard. So with that, we're going to go back to the desk, and we are going to perform a chip-off firmware extraction of this device. So pop back to the desk, and we can immediately notice something that corresponds to what we saw when we were in that terminal environment. So we saw that there were those two separate MTD devices that showed up. Well, here we see two different flash chips, and we can take a closer look at those. We'll do that right now under the microscope. So we got our microscope pulled up here. We're going to get those flash chips into view. Can't quite get both of them in view in one shot, but what I'm going to do is I'm going to get a flashlight and shine the light sideways, and that lets us read these chips a lot better. So here's our first one. Let's put that into focus, and we can read, I can read a few of the first letters on there. This is an MX25L128, and then I can go over on this other chip, and it has the same exact lettering on that flash chip as well. So here we have two identical flash chips, and this is really starting to match that experience that we had on the shell of those two different flash devices that the operating system was able to recognize. So we are going to want to pull both of these chips off. Now, anytime we do this, just the most simple thing in the world, I want to stay organized. So I have observed that there is a notation by this chip up in the upper left side that it says U8, and then down here this chip package is labeled U5. So I've created with my terrible handwriting here a piece of paper. So the last thing you want to do is mix those up and put the chip that has the root file system over where opt is, or vice versa. Now, before I do anything, need to remember to turn off this device and power it off. So I've done that now, and I'm going to get some gloves on because we are going to be using some flux, and you generally don't want to get that stuff on your hands. And I will be using my hot air, station, and I will have some fume extraction going. So that will be what the main noise is in the background. So with that, yeah, I'm going to turn that on, my fume extraction. So we're going to use some Amtech flux here, and we're just going to prep these chips by throwing down a little flux right there and right there. And now I've got my hot air gun. And so we are going to target U8 first. So I am kind of trying to evenly apply heat all over the board, and then specifically on the chip. And we're just going to be patient and not pull up the chip prematurely, because what you'll do is you'll pull pads off of the board, and then you will have problems when you want to go and reattach these flash chips, which we are going to also attempt to do that. Okay. All right, it's starting to move, but it's all right. Now there we go, just like butter. All right, and I'm gonna let that cool off to the side. Excuse me. No, I'm going to put it on my piece of paper so I do not lose track. There we go. Now we're gonna go at this other one. All right. Oh, I just saw some movement. That's a good sign. No, okay. Not gonna force it. Oh man, it is moving. But there's some pin that's not cooperating. And there we go. Okay. Cool, so just gonna let the smoke come off of that one. Actually, I'll put that over there, and I'll take U8, that first chip that we pulled off, and I'm gonna set this board up a little bit. And then we are going to begin the cleaning process on this chip. I'll turn my air extraction off for a second, and we're going to, switch to the microscope camera again. And here is our flash chip. Let's just get that in focus. And now what we're going to do is we're going to try to clean as much of the flux off of this as we can, and then we're also going to get as much of the solder off as we can. Well, actually try to get the solder off first, because okay, so I have some braid here and my soldering iron, and I'm going to just heat up the braid and then touch it to the legs of our flash chip, and this will pull that solder, that excess solder, onto the braid. Yeah, this one pulled a lot off. All right, that side looks good. All right, go to the other side. And if you're holding the braid with your hand, it'll like heat up. So it's always a dance of how long can I hold it with my hand before I burn myself. I've said this in past videos, but it's definitely a rite of passage if you're doing hardware hacking. You're gonna burn yourself. It's gonna happen. All right, I just want to get this one has a bunch on it. All right, that looks good. Now we're going to use a Q-tip and some isopropyl alcohol. And I know it leaves a little residue behind, but some of the little hairs of this Q-tip, but I honestly don't care. All right. We're also going to do the backside here to get any, and yeah, this is where I don't want to touch those things, the legs too much, just because I will really get the cotton stuck on there. But I just want to clean it up as much as I can, keep gunk out of my reader. So now, just to evaporate some of that remaining isopropyl alcohol, I'll just throw some hot air at it. All right, so we have our first chip ready. I'm going to return that to my paper, so I keep U8 and U5 straight. All right, and the next one. So same exact process. Come in here. This one's not wanting to really hold it. I'll try to do the smart thing of not holding it with my hand and getting burnt. We'll see how that goes. All right, I'm actually going to apply a little more flux because this one's being a little more stubborn. And I'm trying to use as much as I can from this small piece of, all right, I'm gonna turn on my air extraction again, because I got that flux coming up. Don't want to breathe that in, if I can help it. There we go. Now we're making progress. All right, now we're gonna flip this around. All right, that is good enough. I'm actually gonna clean this little work surface here. And we'll get the chip back in, clean that off. Other side. Same thing. All right, that looks good. Now we'll hit it with some heat. Evaporate that stuff. All right, and then I'm gonna set it over my piece of paper. All right, so now I have 2 flash chips ready to read. All right, we'll turn that hot air off. Just gonna clean up our surface here just a little bit. All right. Sweet. All right, so I have these 2 flash chips here that I will try to let you see. Okay, so what we're gonna do now is we're going to use the Xgecu T56. So let's just talk a little bit about this reader, because thanks to a lot of you, I have had a lot of new subscribers, a lot of new people watching my YouTube channel. So this is the Xgu T56. This is the super sketchy Chinese site that is the legitimate seller of this device. And so, yeah, this is a sketchy website. Like look at this ad. It says this is the T48 programmer. This is not a picture of the T48 programmer. This is the T56. So, if you don't want to go to this sketchy site to, well, you can't buy it from here. You buy the device on eBay, and then if you want to get the software, these downloads are going to be in the link. Whoever this hero is mirrors all the software downloads from that weird Chinese site, and they drop it in here. So you just go and grab the latest software. You unpack it. It only works in Windows, but there's another wonderful hero that authored this repository that if we go into this folder called Wine, we will see that there is this setup API DLL and there's these instructions. I'm not going to go through them all right now, but this allows you to run this software right here under Wine on Linux, so you don't have to switch to a Windows system if that's something you care about. So, but this is the tool that we are going to be using to read the contents of the flash chip out, and then we're going to analyze them on our Linux machine. So let's go back to our desk and rig up our device. So there are lots of different of these adapters. So I have selected the correct adapter, and the position of the chip, I'll show this when I switch back to the software, but the software actually shows you how the chip is supposed to fit, like where you're going to put it. Because what we're going to see here, let's read U5 first. We're going to notice that when you put this chip in here, like this reader has more space than the chip will fill. And so, well, do you put it at the top, at the bottom? Well, we're going to put it at the bottom. So first, I'm going to show this under the microscope, how this fits in. All right, so we're here under our microscope. And so here, let's get this into focus, is this socket that plugs into the reader. And then we're going to have our flash chip right here. And we are going to place it on the bottom. So we can see up here, there's a pin 1 indicator. So this is the top. We're going to put this in the bottom with the pin 1 position on the chip. Notice this circle right here. Pretty much every chip like this has a indicator of where pin 1 is, which is just a good thing to know if you haven't done much hardware hacking. So now I'm going to push down on this socket and then align all these legs and release, and you can see these contacts go over top of each of the legs on the chip. And again, very cool to have a microscope like this, because then you can verify. This chip is very easy, but there are some chips where the legs are a lot closer together, and you can verify that nothing is bridged, that there's no like solder in the gap between the chip, and we are good to go. So we will go back to desk cam. All right, so then we take this and we place it in the reader. Also on the bottom, there's another pin 1 indicator here that's saying that that this is the top of the reader. And so place that in and we drop this to lock it in place. And then I'm going to plug it in via USB to my machine, and it's going to power on. So, okay, so we're back here at our computer. It has said that the programmer is connected. Again, this is like a running terminal of what it what it thinks is going on. So again, this is a very sketchy piece of software. I know how to do a subset of the things it probably is capable of doing, but we're just going to focus on those today. So the first thing that I've done is I've gone here and I've, read the chip, read the identifier on that chip, and I've punched it into this software. This is actually something I suggest that you do before you ever pull a chip off. If you haven't read that kind of chip before, go into this XGecu software and make sure that the reader can perform the chip read before you just pull the chip off and spend a bunch of effort to do that. And you'll notice here when I punch in this identifier for the device, for this flash chip device, it lists a bunch of different types of that same flash device. And you're like, what does that mean? So this @SOP, @WSON, that is the package type of the chip. So again, if you are new to this, the package just is a physical description of like how many pins are on the chip, how far apart are they, and so there's different standards. So the chip that we have, well, it has 16 legs on it, so we know instantly that it's going to be this one or this one, and we actually want to do this one because we don't care about reading any one-time programmable data off of the chip. And so we are going to select that chip, and now what we're going to do is we are going to perform a read of this firmware. And so I'm going to go to Device, Read, and then you just cross your fingers because you never know what's going to go wrong with this software. Yes, that's always a good sign. So there's a couple things that are going on that make you excited if you see that blue bar start scrolling across. Because we have this option selected down here that says pin detect and then check ID. So pin detect is going to make sure that it can communicate with the pins on that socket that it needs to. And then check ID is actually reading this chip identifier, this hex data, off of the chip that is telling it that it is the correct kind of chip that we have selected up here in the corner. And that's a really high confidence thing that we can look at and say, okay, it's probably, well, like we probably have it fitted in there correctly, and we probably didn't, completely fry the device when we were dumping hot air onto it. And so here we can see that it actually says that the read finished, it succeeded. So we go back, and then we will see some stuff over in this hex editor. Again, I would not rely on the integrity of this hex editor for making any determination. Sometimes when you scroll, it just like freezes up. But it has read it has obviously read data off that chip and is loaded into this area under the Flash tab. So now we have to go and hit Save, and then we're going to save this file to our file system that we can analyze. So again, we're going to call this is U5. Let me verify that and not get that messed up. So we'll just call this U5 firmware, again, because there's the U5 and the U8 identifiers on the PCB. We'll just call it U8 firmware.bin, and we'll hit Save As, and it says it's been saved. And now we're going to go over to that folder, and we can see that the firmware is there, and we can just even try to initially run binwalk and see like, okay, it's cool, it's seeing some of these file systems in there. That's awesome. All right. We're going to go back here now and get this prepped, and we're now going to go back to our desk and swap to the new chip. So again, we're staying organized because we have two identical chips that are off the board. I'm just kind of eyeballing this one. Yeah, like I said, this one you can really eyeball it and not use the microscope, whereas some other package types are going to be more imperative to do that. Okay, back here, and we will go device read again. Okay, it's telling me to check adapter. All right, that's interesting. It's saying I can continue. This is what. All right, I'm just gonna ignore. Yeah, it's always good to ignore the error, right? Yeah, keep going? No, it's not gonna let me. Okay, okay. So I am going to then put this under the microscope, and we're gonna see what's going on. Let's go to microscope. There we go. Okay, it specifically was saying that this. Okay, yeah. Like maybe that's not lined up. I don't know. This is not an exact science, that's for sure. Okay. Because also sometimes I wonder if it's the contact of this, you know, socket within this larger socket here. Then you drop this. Okay. Let's try it again. Okay. Current protection. What the heck? External short. What the? Oh, gosh. Okay. We are gonna show my absolute screw up here under the microscope for you all to see. So I told you that you want to have, I'll take it out of the reader, you want to have pin 1 up top here. Well, I put it backwards. So that's why that's why it passed the pin detection, but it didn't pass the next stage. All right, now we have the chip facing the correct way. Let's put it back in the reader. There we go. Back to the desk. Let's try to read it again, and there we go. It turns out when you don't put the chip into the reader backwards, it has a better chance of succeeding. It's not guaranteed, but it'll help. All right, so here we go. We've got another, flash readout here. So we're going to do the same exact thing. We're going to go and we're going to save it. And so this one is U8 firmware.bin. Save as. There we go. So now we have our 2 firmwares. So let's go ahead and run binwalk-e. So -e, the binwalk flag, is where it'll actually extract. It'll attempt to recursively extract data file systems out of these bin files. And so we're going to do that. And so I have noticed this a lot, especially with the file system type that is on this system. So first of all, these are like you always get false positives like that. That happens all the time. So, but here, this JFFS2 file system, if there's a file system that is that type, I feel like it does a bunch of false positive detections within that file system itself, thinking that it is yet another file system of said type. I don't know why that happens, but okay, so we have finished running binwalk, and so by default, binwalk will place all of the extracted contents in that underscore, file name .extracted folder. And so we can see here that there's a bunch of files. Again, just you can really ignore most of this and then look at these over here. So I'm going to go and look in this first JFFS2 root directory, and there we can see the makings of a Linux root file system. Okay, that makes sense. So I'm going to just do find dot into less, and we're going to look, and we're going to see, yep, there's a bunch of files in there. That's really cool. All right. So we've got, we definitely have some files in there, and that's awesome. So now we're going to go back, and I'm going to go back again, And then I'm going to perform the extraction on this U8 firmware.bin, but then I'm going to show maybe a better way, given this specific circumstance, to extract the data out of this file system. And I'll talk about why. So first we'll run binwalk, right? This is what everybody does. They're just like, okay, I'm gonna run binwalk, attempt to extract that stuff. And it's gonna take, who knows how long. So the underlying command that binwalk uses to perform the extractions on those JFFS2 file systems, okay, it's completed. It's called Jefferson. And that program, I feel like it has problems the way that binwalk uses it, whereas if you can actually carve out where the file system is and then run it manually, you sometimes have a better shot at getting what you want. Okay, and I'll show you why. So let's go into this U8 extraction, and you'll see that it pulled a bunch of these out of here. And then, okay, so like let's say I do a find and then I grep for shadow. Let's say I'm looking for the shadow file, right? You'll see that the shadow file is like listed under a bunch of those. It's repeated throughout, which is not really what is going on the underlying file system. There's just one file system there. There's not, there's not dozens of them. So I have some knowledge from that boot up message. If you remember, there was only one partition on that second flash chip, which now you can see how I'm making an educated guess here, but that this U8 device is actually that second flash chip that only has one partition on it. Well, we can kind of validate that with the file command here and run it on U8. And you can see that it immediately identifies it as a JFFS2 file system, right? And so what we can do is let's just copy this into a test directory so it's clean here. Okay, so we can just run that Jefferson command. Again, this is the underlying command that binwalk uses to do the extraction of the file system. Binwalk doesn't have any built-in file system extraction, to my knowledge. It actually shells out and uses other programs and has a dependency list a mile long. And so this is actually under the hood what is being done. It runs this program, and here, when I run it this way, I get one root file system that is not disjointed, right? Because when you look in that folder, if we went back and looked in that folder, you would see it acted like it saw the shadow file in all those file system extracts. The actual shadow file would probably only be in one of them, and there'd be some just empty file in a bunch of the other ones or something like that, or it would be just a garbled mess. So here we have the actual, okay, it's calling it the root file system, but it just made up that name, right? But this is really that that OPT partition that is the only partition on the disk and is very interesting. And it is interesting because we can look at the shadow file and we can see the root user's password hash, right? So in that UART environment, if we want to get full control of the device, right? If we take it back to a high-level view of what we're trying to do here, we want to completely control this device, and that config user is not doing it, right? That config user is only giving us that limited shell, and we would really like to have the root's password. Now, spoiler alert, this password hash, I threw a bunch of word lists at it, and I could not crack it. If somebody wants to give that a shot, that is on you. But there are some other ways that we can go about using the fact that we can read the contents of those flash chips and write. We could potentially write back to that flash chip. But that is going to be in another video. Just want to thank everyone for coming along this journey with me. Continue to like, comment, and subscribe on these videos, and tell me down in those comments what type of devices you would like me to take a look at in the future. I have nothing for you. Thank you and have a good day.